Kyle Dykman.
Maribel Jaques Nunez.
Matthew Sobel.
Suresh Bandyopadhyay.
Brian Larson.
Adam Dunn from OSER.
Approximately 150,000 total knee arthroplasty procedures take place in the United States every year. Scar tissue forms naturally in response to any wound and often grows rapidly. Therefore, scar tissue naturally develops after knee surgery as part of the body's healing process. Buildup of scar tissue can cause pain and restrict patients' mobility, specifically the range of motion. In order to break down and prevent scar tissue buildup, it is important to move the knee, but after surgery, it is very painful for the patient to actively move the knee and can also cause more harm to the patient. Therefore, it is recommended to passively move the knee to break down and prevent scar tissue buildup. Current methods that passively move a patient's knee are physical therapy and using continuous passive motion devices. A continuous passive motion device facilitates the movement of the patient's knee to reduce the buildup of scar tissue and promote flexibility and normal function within the knee. It is recommended to passively move the knee for 6 to 8 hours a day for 3 weeks after surgery.
Current continuous passive motion devices are very large, bulky, and heavy. They also can be difficult to assemble and to mount onto the leg without assistance. This allows devices to be feasible in a hospital environment in which a patient can receive assistance from trained staff. However, it makes it more difficult for the patients to bring the device home. The most popular continuous passive motion devices all weigh over 23 pounds and are over 36 inches in length. Our goal is to design a device which integrates with the OSER knee brace, the Innovator DLX. By integration with the Innovator DLX, we have several advantages. The brace offers protection and support both when using and not using the device. The patient also does not need to remove the knee brace in order to use the device. The knee brace will allow easier mounting of the leg to the device without the need of assistance. And the integration allows the device to be smaller than current continuous passive motion devices on the market. When we started planning out possible approaches to our device, we looked into several possible mounting options for the brace, as well as the means for driving the prescribed motion from a motor. We looked into a gear system that ultimately used chain rings to drive the motion at the knee. Another system, using cable tension as the means for motion, was looked at for its lightweight setup. Because of their powerful nature, hydraulics were also examined as the necessary torque requirements for varying leg sizes was a rather large and daunting variable. Finally, a drive shaft and foot brace system was proposed in which the motor would power a low-speed drive shaft running up the length of the lower leg to the knee and drive motion at the knee joint. All of these proposals were equally examined and compared based on several key criteria needed for our device. The system needed to be lightweight, small, and provide the necessary power to move the leg as prescribed without exceeding our budget. Upon comparison, we noticed that the safety of the chainring as well as the cable-driven systems were much too uncertain for use within a medical practice on the patient. The hydraulic system was quite strong, but was not very cost-efficient. The drive shaft mechanism proved to be the safest and most efficient means for pursuit on our device production.
We originally used stereolithography, or SLA, to produce the first version of our device. The footrest pictured above is of our original footrest, which turned out to be much larger than specifications. We also used stereolithography to make support brackets and an upper mount which kept the knee brace in line on top. The The brackets and upper mount were designed to slip into the ends of the knee brace without modification to the knee brace itself. Seen here is the second version of our footrest, which was smaller than our original footrest, but was too small to contain the motor or support the forces which were going to be exerted upon it. Kyle, Brian, and Matt focused on the footrest and upper mounts of the device. Agreed concerns with our mentor Adam that the SLA parts were too weak led us to using carbon fiber overlaying in order to reinforce the parts. In the meantime, Soresh and Maribel focused on programming the motor.
Okay, so this is our motor circuitry. We have a computer which puts out Arduino code into the Arduino board. Can you zoom in? And then the Arduino board puts out outputs which go into the pulse, direction, and enable into the driver. The driver puts out the coil currents which goes into the motor. These are connections for the motor. And this is our power supply which connects to the outlet. Puts out 36 volts, about 10 amps, and this is going to be connecting to the driver over there. And we'll see how this all goes.
Pictured above is the first version of the continuous passive motion device. It is built to integrate directly into the Össur DLX knee brace, also seen here. The device would be powered by an electric stepper motor mounted at the bottom of the footrest. The motor delivers power to a drive shaft which runs along the length of the device and applies torque to the brace at the pivot point, causing the brace to bend. Here's the prototype of our device. The drive shaft can be seen attached to the brace running down to the motor. Along with the motor, you could also see the motor driver, the Arduino, and the power supply which powers the unit. Here is where the drive shaft mounts to the top of the brace. You can see here the two bevel gears apply torque to each other, causing the brace to bend. Here you can see the axle of the motor spinning. This axle is what connects to the bottom of the drive shaft and applies power to the rest of the device. This is our prototype in motion. As you can see, as the brace bends, the footrest simply rolls across the floor. The drive shaft currently is not connected and the motor is not powering the device due to kinks in the drivetrain. Our device is not entirely complete yet and still requires a few touch-ups until it is ready to function, as you can see.
Okay, over here we have the Össur DLX knee brace. We can slip off the ends of the knee brace, which are sitting right here, off on the side. And we can couple the knee brace to these brackets on the footrest, which is this design right here. There'd be straps coming out right here. A support for the back of your heel. The footrest is adjustable to accommodate different size feet to width. And over here we have the motor and we have the bracket that the motor drives these gears within this bracket, and these are basically bushings to support your gears. And we go up the drive shaft, more gears coupled here, and we have this this mount which inserts into the top of the knee brace. Also, we have these wheels which attach in the back right here, just like that. And that is our design.